So let's begin with Patryk and talk about teleportation, please.
Okay, so hello everybody. My name is Patryk, and today I will tell you about a recent result we had with Paul Skrzypczy, which is also in this audience. So the result concerns quantum teleportation, and in particular a certain extension which we call catalytic quantum teleportation. Okay, so before we begin going into the details, let me just briefly remind ourselves the standard teleportation protocol. So, as introduced in 1993 by Bennett et al., the protocol of quantum teleportation essentially concerns two parties, Alice and Bob, that are spatially separated. So they share an entangled state rho, and Alice is given some unknown state, gamma, and is asked to do something in her lab along with Bob, employing some classical communication, so that the final state on Bob's lab is precisely the same as the input state she received. So the goal essentially is to simulate a quantum channel to the best of their possibilities from A to B. So the goal is to make this green channel phi as close as possible to the identity map. So how can we quantify that? So the standard way to quantify it is by the fidelity of teleportation. So what we do is we essentially sample input states on Alice's side randomly, let's say according to her measure. We give it to Alice, she makes her measurement, let's say, she sends the outcome to Bob, who then applies some correction operation. He may send back some communication to Alice, and they may play this game as long as the final state on Bob's lab is close to the state to be teleported. Okay, so this quantity is essentially quite difficult to compute. However, it was found that a much simpler expression exists, so a much simpler formula, which concerns eventually just two quantities. So the first quantity is the quantity F, is the entanglement fraction, which quantifies how much entanglement do they share, and the local dimension. So this is the dimension of the state to be teleported. So as you can see, so the larger is the dimension of the state that we have to teleport for a fixed entanglement content, the harder it is to teleport these states. Okay, so with this, let me now stop for the moment talking about teleportation and tell you a bit about something we call catalytic extensions of QIP protocols. So in general, when we think about QIP protocols, what we imagine is a certain task that quantifies some fundamental trade-offs in nature. So, and those trade-offs, we can capture them by looking at all possible outputs that our protocol may provide. So these outputs are essentially quantified by everything that is possible under quantum mechanics, right? So this orange blob essentially means everything that we can achieve under quantum mechanics. Okay. But now there comes our scenario constraints. So our protocol has some limitations, like locality, like no signaling, and this scenario constraints, they further impose new constraints to the results of the experiment. And the intersection of these feasibility regions is essentially everything that we can achieve in our protocol. Okay, so this orange region is our protocol. So now, for example, in teleportation, those restrictions are just local operations, classical communication, and shared entanglement between Alice and Bob. Okay, so in general, this is what our protocol consists of. And now, the protocol essentially requires some resources to run, to fuel it. So what we can do, despite using some additional resources, is that we can add new set of resources, which eventually are not destroyed during the protocol. So they remain the same initially and after the protocol. So this as a whole allows us to look at catalytic extensions of protocols, which essentially try to get out of this orange region and lift certain restrictions, either those imposed by quantum mechanics or those imposed by the scenario itself. So this is what we will be trying to do for teleportation. And here we see some results which were going into this direction in the recent years. Okay, so we have our teleportation protocol, and now what I precisely mean by catalytic teleportation is the following. So I assume that Alice and Bob now share an additional state. It's another bipartite state they share, and they can do whatever they want with that state. However, they are asked to leave the state exactly the same as they received it. Okay, so now this is very simple. So this is just another state which comes into our protocol and another set of constraints. So now, if we want to quantify performance in a fair way, what we can use is, again, we can use fidelity of teleportation. However, now we have access to this additional state. So what we do is we allow Alice and Bob to choose the best state, the best state of the catalyst they potentially can choose. Okay, so we optimize over all such states, and we demand that this state is not changed by this LOCC protocol. Okay, so this is it. This is the catalytic protocol. So now let me mention our main result, and I will discuss it a little bit further and give you the explicit protocol which achieves this result. Okay, so what we've shown was that for any bipartite quantum state row that is shared between Alice and Bob, the catalytic fidelity of teleportation can be essentially lower bounded by the quantity that you see here. So surprisingly, it looks very similar to the standard teleportation quantifier, with the only difference that this entanglement quantifier F is replaced by a reg, something which we call a regularized entanglement fraction. So this is the definition, and this is further the definition. And just to give you some insight what this quantity represents, let's look at it. And imagine that our Alice and Bob, instead of having just a single copy of the state that they share, they have n copies of that state. So we multiply their state, and we allow them to apply some big LOCC operation on all of those copies. Okay, so they apply it, and now what we do is essentially we calculate the overlap of every pair with the maximally entangled state. Okay, so and we calculate the average of the overlap. So we calculate the first overlap, the second one, the third one, and the last one, and we look at the whole, and we average over all these overlaps. So in a sense, this is the quantity that we want to optimize in our protocol now. And as we can easily see, is when we take this channel E to be just a separate collection of channels on each copy, then our fidelity, catalytic fidelity, will essentially be the same as the standard fidelity of teleportation, meaning that this quantifier is always equal or larger than the fidelity of teleportation. So basically, the basic question is: can we ever achieve something better? Can we ever achieve a performance that is better than the standard teleportation fidelity? Okay, and so as you may expect, this is the case. But before I show you this explicit example, let's look at the explicit protocol that achieves this lower bound. Okay, so we have our teleportation protocol, and now we decompose this LOCC map into two steps. So the first step is something we call a catalytic preprocessing. So this is a subroutine which essentially boosts the entanglement that we have in our state to something bigger, right? So intuitively, you can think of this as a way of reshuffling entanglement in the joint state of rho and the catalyst in such a way that the properties of entanglement that are useful for teleportation are improved on one part of the Hilbert space. The nice thing about this subroutine is that it's completely independent of teleportation. So we can apply it to other protocols to improve the entanglement fraction, and it will work. So once we do that, we just it just remains to apply our standard teleportation protocol, which achieves this this fraction, and we are done. We basically achieve the lower bound that I told you about. Okay, so now let me give me a very simple example, which essentially demonstrates how this performance or how this advantage can be exploited in the best possible way. Okay, so suppose our task is to teleport quantum states of dimension 3. So we want to teleport Q trees. However, what Alice and Bob have in their lab is just a maximally entangled state of dimension 2, local dimension 2. Okay, so even though they do everything perfectly, they may never achieve the perfect fidelity of teleportation, right? And if we do the calculation, then we will see that in the numbers. So it turns out that the fidelity is roughly 0.75. So if they look at their channel as well, as their protocol as a channel from A to B, it will essentially act as an identity in 6 out of 8 cases on average. Okay, so what about the performance of the catalytic protocol? So it turns out that you can find a catalyst, a special entangled state, which essentially, if you apply this preprocessing technique that I told you about, allows to boost entanglement fraction in the shared state. And this you can do up to 4/5, which essentially gives you a much larger catalytic fidelity of teleportation. Okay, so this is a lower bound, meaning that it's an achievable performance, but we haven't proven that it's the best one. So this is something you can achieve using a well-tuned catalyst. So if you look at the joint channel, at the effective channel acting from Alice to Bob, what you would see is that it acts as an identity in 6 out of 7 cases. So this is strictly larger than what we ever could do before. Okay, so just to show you that this is really not some mathematical curiosity relevant only for the maximally entangled state, here I plotted the catalytic advantage. So each point in this triangle corresponds to some pure shared state between Alice and Bob. Okay, so here in the corners we have a product state, just one Schmidt coefficient. In the middle we have the maximally entangled state for dimension 3, and the color corresponds to the advantage over the best standard teleportation protocol. So our EPR state that from the example is precisely at the middle of the edge, and as we can see that around that point we still have infinite number of states that can demonstrate advantage, and this is really generic, meaning that almost for every state that you can think of, you will find some catalyst that will improve your performance even further. Okay, so we're almost there. Just let me mention one thing which should be mentioned to be fair with you. So of course the protocol has certain limitations, and something I didn't tell you about is, although we require that the state of the catalyst remains unchanged, what we observe is that the protocol introduces some correlations between the catalyst and the states that are teleported. Okay, so this can be a problem. So it will not be a problem if you want to teleport states, let's say n copies of some state, and using the same catalyst, and you are just interested in the marginal. But it will be a problem if you want to preserve the product structure of your state that you are teleporting. However, what we also managed to show is that you can make this error or these correlations that are produced between the final state and the catalyst arbitrarily small. And the price that you have to pay is to increase the dimension of the catalyst. So as long as it is big enough, you can make it arbitrarily small. Okay. So with this, let me conclude. So what I described to you right now was a catalytic extension of a teleportation protocol, and hopefully I convinced you that the protocol essentially shows that quantum catalysis is a useful tool to improve transfer of quantum communication. What I also told you about was a little advert to look at extensions of quantum protocols from a catalytic perspective. And for that particular problem, we found the general technique which allows you to boost entanglement and reuse the state in some other process with the hope that it will have better properties. Okay, so with this I will finish, but just let me give you some take-home message. So the intuition we have, at least we found from this paper, from this result, was that quantum catalysts essentially act as perfect reference frames. And by this, by reference frames, I mean that in a certain sense, in a precise sense, they allow to lift certain limitations imposed by the constraints of the protocol. So if you have a protocol, you can use a catalyst, a finite catalyst to lift certain restrictions it imposes. And they are perfect, meaning that unlike ordinary reference frames, they experience no backaction. Okay, so with this, let me thank you for the opportunity to share these results, and I'm happy to answer any questions.
Thanks a lot for a very nice talk. So I think the question of whether correlated catalysts are useful for operational tasks is very relevant. I'm not 100% convinced that you're still not comparing apples and oranges, though.
Oh.
So I mean, the reason is because the entanglement fraction isn't resource monotone, right? So the combined system, catalyst and the state you want to use as a resource, that entanglement fraction can only go down.
Mm-hmm. That's true.
But somehow this doesn't come out in your results. So what's your intuition of why this doesn't?
Yes. Okay. So my intuition is that so essentially what is important is, I mean, when it comes to entanglement, it's not like not only the average properties of entanglement, but like the whole distribution of let's say Schmidt coefficients, and in particular in teleportation, it's a very particular monotone, which is like, let's say, the entanglement fraction, which is equivalent to one of the Renyi entropies. I guess it's 1/2, which plays particular role. So in this sense, the overall LOC operation, which acts on our initially product state and ends up in some correlated state, it does not change the entanglement fraction of both. Right. So the entanglement fraction is preserved. So what we observe is essentially that having access to this catalyst essentially allows us to redistribute entanglement in the joint state, the catalyst plus the system, in such a way that the relevant part of the entanglement is pushed onto the state. So
yes, I guess my question is somehow if you would at the very end use your catalyst also for a teleportation itself.
yes.
If that, then the advantage would still be there.
What do you mean? Can you say that
maybe
again?
we should take it offline, but thanks again for the very nice talk.
Thanks for the question.
Yes, indeed, it was a very nice talk. I don't know what my question is tonight, but you have found a low bound, right, on
Yes,
the
that's
fidelity.
lower bound.
So do you have, is it a reasonable question to ask as to what sort of quantum states would act as better catalysts than others?
Yeah, that's a perfectly valid question. Again, that's a very good question. So in our case, we found that. So what we wanted to look for is a catalyst that is universal. So we were looking at the family of catalysts that can essentially improve performance for any possible state that is shared between Alice and Bob. But it's a perfectly valid question to ask, well, given this fixed shared state between Alice and Bob, can I find an even better catalyst that is well suited for this particular problem? So this is something we haven't looked at, but I guess it's a very interesting direction to further pursue.
Thanks.
Very nice talk. Do you have examples of states where this regularized fidelity is actually a singular quantity? So where the limit goes away?
You mean the correlations, right?
So you had this regularized fidelity quantity, right? The limit of this Fn divided by n, right?
Okay, so
yeah, here. So do you have examples of states where this is not actually necessary to do?
You mean that even though, okay, so you mean that you cannot achieve any advantage even though you.
I guess that it would, yeah.
Yes. So, okay, so here what we see, basically on this triangle, what we see is that, well, the maximally entangled state, which you have here, well, you cannot improve it further because it's already the best thing you can do. And here we found like a line of states which also doesn't. So this regularized entanglement fraction is just the same as the standard one. But we don't understand really. I mean, it's really a thing that we have to look at in the next step, but we don't really understand why it doesn't work for these states.
Okay, thanks. Got it.
Hi, I have a very tiny question. I missed in this example, what is the dimension of the catalyst? Like, what kind of state is this catalyst?
So that's a good point. I didn't mention that.
Yeah. Okay.
So, in fact, I mean, to achieve this regularized entanglement fraction, you need to take the limit of n going to infinity. So basically, the dimension of the catalyst goes to infinity, right? However, also, if you're interested in the paper, we have an example where this catalyst is a Q-treat. And then you can still demonstrate some advantage, but it's much smaller. So right now here, this is basically 12%. For the smaller catalyst, it's like 2 or 3%, and it scales with the dimension. So the larger catalyst you use, essentially, the more power you get for free.
Okay, but you can start with 3 and you get already advantage.
You already get something. Yes.
Okay, thank you.
Hi, very nice talk. I had a question. If you go back to the pre-processing, the slide with the pre-processing step,
Okay.
could you say a bit more about what this pre-processing is?
Yeah. So okay. So basically, it's an LOCC operation which will act only on the system and the catalyst. So that doesn't touch the state to be teleported. And what it does is essentially, so what we do is basically we take a very particular state for the catalyst, and it turns out that if you tensor out, like technically tensor out the shared state with the catalyst, what you will see is in the joint space of the state, you will see like you will be able to measure. Okay, so the catalyst is composed of a quantum part and then like a classical flag. And such that if you look at the product state, what you would see is that after measuring the flag, your total state of the system plus the catalyst will be in a very in some particular state. And in some of the cases, the state will be looking almost exactly like the n-copy state of the system. And if that is the case, what you would do is you will apply this a big LOCC operation acting on n copies of the state and transform it into something with with the same entanglement content, but distributed in a different way. Then if you average over the flag, you will see that your catalyst is exactly the same as it was, but the state of the system have changed.
Okay.
And this is precisely what gives you the power.
Now, I guess this is a question more about, is there something known about getting more entanglement into rho AB if you have, say, multiple copies of rho AB tensor omega CC prime? So basically catalytic distillation of entanglement for rho AB. Do we know something about that? And are we doing something similar or separate from that?
Yeah. So I think that's a very good point. So I think you can look at this from this perspective. So for catalytic distillation, you might ask, okay, so if I can distill K+1 copies, but I can't distill K copies, what can I do? So then you can, let's say, take the catalyst, you can find a catalyst which essentially allows you to distill these K copies only using the fact that you are able to distill K+1 copies.
Okay, maybe we should talk more offline.
Okay.
Thanks a lot. Thanks a lot.
Let's thank Patryk again.